So, on last lecture, we kind of did some analysis using the grand canonical ensemble. We had this phase transition, phase equilibrium, and we had an introductory discussion of phase transitions, and we looked at the oscillation, the fluctuations in the number of particles and the energy in the grand canonical ensemble. Well, that kind of basically completed our discussion of the classical statistical physics. Classical in the sense that although we dealt with quantized energy levels, we didn't actually give a full quantum mechanical description of statistics. Well, before starting the quantum mechanical description, I would like to study the equipartition theorem first. Again, a classical result, and then we will see what we can do in full quantum mechanical description. So any questions before we start the equipartition theorem? So let X be any position xi or momentum. I have this n particles, they have positions and momenta. X is any one of them. And let's calculate xi del h by del xj in the canonical ensemble. Its expectation value. Well, the definition of the expectation value is just sum over all possible microstates of xi del h by del xj, let's say microstates, times the probability of the microstate. This is the definition of the expectation, the average of that quantity. Well, in the canonical ensemble, the probability is given by e to the power minus beta, but whatever the expression of the energy is, Q, it can be a function of Q and P. Sum over microstates will be integral over all momenta and coordinates. So I'm writing dp and dq. This is actually a 6n-dimensional integral. dp meaning that all the components of all the momenta, dq meaning that all the positions of all the particles. And then the probability will be this divided by the partition function, which is nothing but the same integral without the xi del h by del xj. Well, I can write that derivative of the Hamiltonian as the derivative of the exponent with respect to xj. The derivative of the exponent is the exponent itself multiplied by the derivative of whatever is in the exponent. Well, there is a minus beta, an extra factor of minus beta, so let me divide by minus beta. Now I will do an integration by parts. This is minus kt. This factor is 1 over minus beta. Let me write the q over there of derivative with respect to xj of xi times that exponent minus the exponent times derivative of xi with respect to xj. Well, this term over here, whatever xj is, it can be some position coordinate or some momentum coordinate. If I integrate over that coordinate only, it will just give me e to the power x times e to the power minus beta times h when that particular coordinate is at infinities. But that is 0. Infinity will be either very large at a very far away distance. Eventually we will be taking the thermodynamic limit, so if it's a very far away distance, that exponent will be 0. And, if it is in a finite box, if xj goes from minus infinity to infinity, that basically means that the potential outside the box is infinite. If the potential is infinite, h is infinite at infinities, so that exponent will be 0. If xj is some momentum, well, the limits of the every momentum coordinate is minus infinity or plus infinity, then the kinetic energy will be infinite. So that term will basically give me 0, whatever xj is. It can be a position coordinate or a momentum coordinate. That derivative with respect to xj, when we integrate it over xj, this will be 0. There will be no contribution from that boundary terms. And so what remains is for this average value will be, well, let's look at this derivative over there. You see, different coordinates and different momenta are independent of each other. So if I and j are different than each other, that derivative is 0, because xi and xj, they will be independent of each other. If you take the derivative of one with respect to other one, you just get 0. If I and j are equal to each other, well, that derivative is just 1. So that derivative is actually Kronecker delta ij. So what this gives me is, with this minus sign over there, I get a kt over q dp dq e to power minus beta h, there Kronecker delta ij. Well, Kronecker delta ij is just a constant. I can take it out of the integral. But this integral over there is nothing but q. So q's cancel. What gives us is xi del h by del xj is equal to kt Kronecker delta ij. Again, I repeat here, xi or j can be any position or momentum coordinate. In fact, it can be anything, whatever that is. Any one of the things that you are integrating over and summing over the microstate, this result will always hold, whatever xi, xj, and whatever Hamiltonian you have. Now, let's look at a particular case. Let's say that we have well, let me just say the terminology. Assume h is a homogeneous function of its arguments of degree 2. Is this terminology familiar from mathematical methods? Is this terminology familiar to you? You see, what this means is h will be a function of p and q. If you multiply its arguments by, let's say, lambda, this will become lambda squared h, p, and q. This is what is meant by a homogeneous function of its arguments of degree 2. If it was of degree 3, it would be lambda cubed. If it was degree 4, it will be lambda to the 4. Well, what does this tell me? Well, let me take the derivative of both sides with respect to lambda. So it will be derivative of Hamiltonian with one of the arguments, the first argument, second argument, whatever, times derivative of that argument with respect to lambda. But the derivative with respect to lambda of that argument will be just the argument itself. You see, if xi is sum of the coordinate, the position arguments, then the position argument will be lambda qi. If I take the derivative of lambda qi with respect to lambda, I just get qi. But this is equal to, well, let me write it more explicitly if you like. This is derivative with respect to lambda xi times derivative of lambda xi with respect to lambda. This will be equal to 2 lambda hpq. But this is, and let me also evaluate this when lambda is equal to 1, which will give me, well, this is just xi derivative of the Hamiltonian with respect to xi is equal to twice the Hamiltonian itself. Now we can see it, let's as an explicit example, this is, let's say, p squared over 2m, p1 squared over 2m plus p2 squared over 2m. Then the only contributing factors here will be the derivative with respect to p1 and p2. p1 times the derivative of the Hamiltonian with respect to p1 plus p2 times the derivative of the Hamiltonian with respect to p2. This will be p1 times p1 over m plus p2 times p2 over m. This is p1 squared over m plus p2 squared over m, which is twice my Hamiltonian. Now let's come back over here. Of course, here keep in mind that I'm summing over I. I will not be writing it explicitly, but when an index is repeated twice, you are just summing over it. Like over here. This is for the first index, this is for the second index. So what we obtained, the average of xi del h over del xi should be equal to twice the average of the Hamiltonian of the system. Well, this is nothing but Kronecker delta I kt, and keep in mind that I'm summing over all I. The right-hand side is nothing but twice the energy of my system. So U is basically 1 over 2 kt times, let me call F. F is equal to the number of quadratic terms in the Hamiltonian. This is the so-called equipartition theorem. Okay, for the equipartition theorem to hold, keep in mind that this condition should be satisfied. Only if we have terms that are squares of momenta and coordinates, or products of one momentum and one coordinate. Even in that case, the Hamiltonian stays a homogeneous function of degree 2. And I repeat, this is our general result. Basically, equipartition theorem is just an application of our general result. Now, let me look at something else. Let us consider the positions of particles making my system times the forces acting on my particle. Let me take their average and sum over all the particles. It's just position times the force. This is called the virial. Just a name, historical name given, that's it. Well, why is that important? Well, let's just consider non-interacting particles. Then the forces acting on my particles is just, the Fi will be non-zero only for particles close to the surface, because there is this bounding box, and that box is exerting forces on my particles. So this virial is just the sum over particles on the surface. Well, this is just sum over all are on the surface, all positions on the surface. Now, the position of my particles are at R, dot product with the total force acting on all the particles at that point R. Well, just let's say that this is my surface, this is my volume. I can pick up some point on the surface. Well, let me pick this one. If I enlarge it, it will be this area. There are all these particles right at the surface, colliding with it. Well, the surface will exert forces on all these particles perpendicular to the surface. These are my Fi's. And my Fr is just sum over all these Fi's for particles at the position R. This is what I mean by Fr. Now, whatever force the bounding box is exerting on my particles, I have let's say that this is my ideal gas, and this might be the piston, a gas confined within a piston, for example. We have seen that the ideal gas has a pressure, which basically means that the particles, as they are colliding with the surface of whatever is binding my system, is exerting a force on the surface. And this force is the force that the surface is exerting on my particles. Well, a better notation would probably be dF, because I will be taking a very small, see here, I have taken a very small area so that all those particles I can treat as if they're at the point R or very near R. Now what I will do is, I know what dF is. dF is minus the pressure times the area. Whatever the pressure my gas has. That pressure is the force per area that the gas exerts on the confining box. So the box exerts minus that force. And summing over all points on the surface would be just integrating over the surface. It's a closed surface, r dot dA. But now I can use the divergence theorem. This is nothing but minus P times the integral of the divergence of R over the volume. But divergence of R is just 3. So the virial, at least for this particular case, is minus 3 times P. Remember, I also have this expression. Well, now let's relate those. Remember, the definition of the virial was sum over all particles Qi times the force acting on those particles. But the force is nothing but Pi dot, the rate of change of momentum. But Pi dot is nothing but minus the derivative of the Hamiltonian with respect to Qi, the corresponding coordinate. But this is what I had obtained. So this is equal to minus sum over all I kt Kronecker delta I summed over all the coordinates. Which is equal to, well, essentially I is labeling the coordinates. I have 3n coordinates. If I have 3n coordinates, this will be minus 3n times kt. And hence we have minus 3p, sorry, this is minus 3pv. 3pv is minus 3n kt, or pv is equal to n kt, just an alternative derivation of the ideal gas law. Now just pay attention to something. You see here, I started with writing particles on the surface, because for other particles Fi is just 0. Here, so in this sum, what contributes is only the particles on the surface. I come over here, Pi dot. I'm summing over all I, well, some of them will be 0. But when I take the average, you see here, all the particles will contribute, because on average, every particle will collide with the surface at some point. So here, Although only the particles on the surface will collide, will contribute to, due to this Fi, when I use this one, that is when I actually take the average, well, all the particles will contribute. That is why I have 3n over here, for the 3n position coordinates of all the particles, not just the ones at the boundary at a given moment. You see, when I'm doing these, when I'm calculating this one, I'm looking at a moment. At the moment, Fi will be non-zero only for particle. Well, okay, so actually let me just remove this. That's not the average. At a given moment, I'm just looking at the product of the position of particles times the force acting on those particles summed over all the particles. At the moment, only some of the particles will be feeling a force. So that sum, I'm not taking any average, will be equal to minus 3 times PV. Again, I repeat, I'm not taking any average. But when I take the average, this is correct, whatever I and j is, whichever particle I'm talking about, that average will always be kT times the Kronecker delta. So that is what I used as I go from this step to this one. Yeah. When I went from this step to this one, I'm just saying that I'm not looking at a particular moment, I'm taking an average over all the particles and over all the time, in a sense. And so here in this sum, I have sum over all particles. And hence I have a 3n over here. So any questions?
So the definition of the virion didn't have an average?
Well, I don't remember the exact the conventional definition, but just for consistency in my notation, let me remove that average over there. Since we are in a canonical ensemble also, things don't actually fluctuate much.
So because when we write like the average of the virion, it implies that there is a non-average virion?
Yeah.
Hocam aslında sanki ben böyle konuşuyorsun bakınız. The alternative relation between kinetic energy and potential energy. This
Not within this context. Well, of course, you can still, let's say, if you apply it to non-interacting particles. No. Let me just leave it. For example, if you look at the harmonic oscillators, what is the average of the kinetic energy for this case? Well, the average of the kinetic energy will be Pi, let's say Pi Vi over 2. This is the average kinetic energy, which will be 1 over 2 the average of Pi del H over del Pi which will be 1 over 2 Kronecker delta I times KT, 1 over 2, 3, and KT. This is the kinetic energy. Well, what about the potential energy? For the oscillator system, let's say. Well, this will be 1 over 2 Yeah. U is 3 and, sorry, this is 2. U is 3n kT. Well, there are 6n quadratic terms, each one contributing kT over 2. This will be 3n kT, which is twice the kinetic energy, if you like. But I mean, this is kind of true.
In the first line, we have a velocity R.
Yes.
But we wrote H over VI, which will give QI. Okay. I thought we should write some kind of derivative of QI.
Yeah, that's QI dot. The time derivative of the position is the derivative of the Hamiltonian with respect to momentum.
The Hamilton's equation was giving QI right? Not QI dot.
No, QI dot. We have
Okay.
QI dot is del H over del PI, and PI dot is minus del H over del QI.
Okay, I found that one slightly wrong.
So that kind of completes our classical, let's say, statistical mechanics. And in the next hour, we will start with the quantum statistical mechanics. You see, although we did use quantum mechanical systems in our earlier discussions also, we looked at the energy levels of the quantum mechanical harmonic oscillator, or we looked at the energy levels of the quantum mechanical magnetic dipole, etc. But we use the concept from classical statistical physics and just use the quantum mechanical nature in counting the number of microstates our system has. We didn't really formulate a quantum mechanical picture of statistics. And there are a couple of conceptual problems that we should address. Like, for example, in quantum mechanics, we talk about energy eigenstates, which do not change in time. But in classical statistical physics, we are always using the concept of the system is changing in time, everything is changing, the systems are exchanging energy with each other, and hence the system reaches some kind of an equilibrium. But in quantum mechanics, if you create an energy eigenstate, the system never changes. So how will we reconcile this? Well, we will discuss in the next hour.